Welcome to Fabrity Talks podcast, where we explore software development, generative AI, industrial IoT, and data engineering. Our goal is to provide IT executives with practical business insights that can be seamlessly put into practice in their organizations. You can listen to every episode of our podcast on Spotify, Apple Podcast, Amazon Music, and YouTube. If you want to know more about what we do, visit our website at fabrity.com. Now, let's get started.
Hi, welcome to the new episode of Fabrity Talks podcast. I'm your host, Jarosław Ganczarenko, and today I'm joined by Dr. Marek Drewniak, Research and Development Manager at AIUT, and we'll be talking about the exciting topic of mobile robots in intralogistics. Hi, Marek. I'm happy that you accepted our invitation.
Hello. Hello, everyone. Thank you for invitation, and I'm glad that I can be here.
Great. So I must say that the topic of autonomous mobile robots seems incredibly interesting to me because in our podcast, we already covered various modern industrial technologies and tools. But for the very first time, we will be discussing something that is, I would say, a tangible proof of what Industry 4.0 looks like in practice. So before we could start, could you say just a few words about your professional backgrounds, about your robotics experience, and about what you do at AIUT, your company?
Yes, thank you. As you mentioned, I am head of research and development section in AIUT company. AIUT company is a technological company providing various solutions in automation, control, robotics for industry, widely understood. Our main scope of activity is delivering services and production lines, which are responsible for manufacturing, widely understood. And one of the activities that we hold in our company is production and commissioning of intralogistics systems based on autonomous mobile robots and automated guided vehicles.
Okay, great. So, but you are based in Poland, yes? But you have also the companies that
Yes,
expand to
indeed.
foreign markets.
Indeed. The headquarters of our company are located in Poland, in Gliwice city, southern region of Poland. However, we have distributed companies also in other countries, including Northern America, like United States or Canada. Recently, we've been opening our new office in Mexico as well. Then Germany, Romania, China, India. So we can say that we work globally for actually various types of customers from industrial field. Yeah.
Good. But could you say more about your professional background, your story, why you choose robotics as your main point of interest, why you specialize in this topic?
Yes. As for me personally, I think that the main point why I decided to do this is like I always treated programming of automation control and robotics as a final step of building solution from like bricks. You can create a construction, then you add electrical wiring, and then you put a light into it by writing a software that makes it operable somehow. So this is something that I have always felt works great for me, and I do really enjoy it. Truth is that if you want to be an engineer in fields like this, you have to like it somehow. So this is definitely one of the things that works for me here. And as for my presence, I started my professional work with AIUT some years ago, and through fields like automation control, electronics, industrial informatics, I reached the point in which I am now. My section and this activities that I do at work are somehow the combination of all the mentioned fields. So with things like this, you never get bored, and this is something that I do really like. I appreciate it, and that's a great opportunity for not only the development of technological solutions, but also for self-development. So, yeah, this is why I'm here.
Yeah, so I can say that you just combining the physical world of machines with the digital world of software that powers these machines.
Exactly. This is exactly what I do.
Okay, so given the fact that you're an expert in robotics, maybe we could start with the basics. Could you just explain more what are these autonomous mobile robots? So the acronym is AMR, and automated guided vehicles, so IGVs, and what are they used for?
Yes, AGVs and AMRs are type of mobile units widely used not only in industry but also in communal areas, for example. These are vehicles that were designed initially to perform transportation tasks, like to bring goods between specific points. As for AGVs, they were developed some time ago, and formerly these units were working based on the navigation system that was based on the following of something, which means
Hmm.
in order to perform the movement, they needed to have some kind of, you know, perception that enables identification of, for example, magnetic tape or some markers that were spread around the environment in which they were working, and therefore this is why they are called guided vehicles. However,
So
the
there is
during
a
the
sorry to interrupt, just to say it clearly. There's a magnetic type that is on the floor, and the robot moves along this type.
Exactly. This is exactly what I mentioned here. I believe that we'll be talking about various navigation systems in a moment, but the very first implementations of such units were based on detection and following of the tape or some kind of a carrier that was sticked or glued to the floor, or, for example, that were distributed in the environment, sticked to the walls or somewhere else. Yeah, and
Okay.
during the developments, a new type of units evolved. They are called AMR, autonomous mobile robots.
Hmm.
They were developed in order to provide some kind of autonomy for the mobile units, especially for giving the possibility to make decisions what exactly the unit can do when it's en route. So this autonomy makes robots suitable for different types of applications, since they can make up their own decisions, they can cooperate with the environments, they can cooperate with human personnel. And this is something that is being developed recently. We're mostly talking about AMRs, not AGVs. AGVs was the first stage of these mobile units that was started some time ago. So this is the main difference between them.
So the future belongs to MARs. Okay, so what are the main areas where these mobile robots are used?
Formerly, the very first area in which such robots were developed was industry. As the industry exists, there was always a need to provide a transport between specific points on site. For
Hmm.
example, there was always a need to deliver components from warehouse where these components were stored and production stations where these components are used. Later, this evolved. Recently, we observe a trend related to so-called Industry 4.0, in which manufacturing needs to follow specific customer demands. As you probably are aware,
Hmm.
customers more and more often, have the possibility to customize their final products. And this forces that manufacturers need to equip their system with functionalities which will enable this flexible and adaptive manufacturing. For example, for quick recalibration of production elements, components, systems, and so on and so on. And since this approach is present in manufacturing, the traditional production using the stationary production lines, like technological flows, sometimes is not suitable for such a flexible approach. And this is the area in which perfectly AMRs and AGVs can fill this gap. AGVs and AMRs can be used as a transportation carriers for manufactured goods themselves. You can put the product that you want to manufacture on top of this AGV, and this AGV or AMR can bring this good through the stations according to current state of the shop floor. For example, we can observe that some of the stations are not operable at the moment, so we can skip them, go somewhere else. For some products, variants do not require that products should go to the station. So again, we can skip this. This use of AMRs as transportation carriers provides this great flexibility. So this is area in which they are observed to be implemented more and more. But aside from the industry itself, AMRs are also used in communal spaces, like, for example, hospitals, where they can be used for transportation of medicines between rooms, or in offices. Perhaps you also had a possibility or opportunity to see robots delivering food in restaurants. So this is also the place where they can be used.
Not in
So yeah,
Poland. Not in Poland.
Yeah, no, in
Uh,
Poland. Actually, in Poland, I saw
yeah.
it in one of the airfields. I think it was Krakow. There is a
Okay.
restaurant in
Interesting.
which there is such solution. What I want to say is that due to its universal capabilities to transport, it can be used actually everywhere when some basic requirements, for example, regarding the floor or surface on which it's moving, are met. So possibilities are very wide. But from my field, we base on this industrial aspect. So this is what I am familiar with, and this is what I do personally.
This is very interesting what we are saying about this custom production, because there is no anymore a long series of similar products, but small series of customized products that are customized to the specific needs of the target customer. So this is the use case where these AMR robots work well. Okay, I want just to go more into details and just to explain why this, apart from this flexible manufacturing model, why this AMR and AGV's robots are gaining popularity now in the industry. Could you just give more detailed
Yeah.
insight into the reasons?
Mhm. I would categorize the reason into three groups. The first one is related to technological development. The main aspect that makes AMR so popular recently is the rapid development of computational power of onboard controllers, which can be used inside of such robots. Like 15 years ago, the main type of the controller used within industry was something that is called programmable logic controller. Aside from the specific architecture of such controller, its main objective was to perform stable process. So it's safe, deterministic, and stable. But the main disadvantage of such thing was that it wasn't capable of performing a lot of calculations. And recently, in like last 10 years, there was a rapid development of industrial computers that right now are widely used in industry, which based on the architecture of computers that we use daily, like in offices, taken directly from IT solutions. And thanks to this computational power, we finally can manage, we can store, we can process large number of data, which then can be used for, controlling over the process, for using AI for AI purposes, and so on and so on. So computers is the first thing. The second aspect here is rapid development of scanning solutions, which
Mhm.
increase the perception of mobile robots and automation control solutions in general. What I
So
mean is that
basically, what robots can see. Yes.
exactly. I'm talking about scanners, about sensors, about cameras. Recently, also due to the fact that this computational power has increased, such devices were developed rapidly, and they can not only monitor spaces in a way that provide huge amount of details and data related to this environment and surrounding, but also they can, process this data in order to calculate something. To be exact, in the case of AMRs, one of the most commonly used solutions for scanning of the environment is a scanner based on light detection and ranging. The abbreviation is LiDAR. And this LiDAR simply uses the time of flight, measures the time of the emission of the light from the device. And when this beam of light hits the object, it comes back. We can calculate the time needed for the flight of this beam, and thanks to this, calculate the distance to the object. This is done in a rotary form, so the device turns around continuously and scans the surrounding all the time, which is incredibly fast. This provides, thousands of monitored points around of the device, and you need to have device powerful enough not only to collect this data but also to process it nearly at
So
the real time.
so LiDAR technology is the same technology used in the autonomous or self-driving cars.
Yeah. Yep. This is exactly the same technology. As you mentioned, it's also not used that much in. I mean, it's not only in the industry, but also for the automotive, or for example, scanning from aeroplanes, bathymetry in seasides. Or yep. This is exactly the same
Okay.
technology. Yeah. So scanning devices, and the third technological aspect is development of battery technologies. This results strictly from automotive aspect.
Mm-hmm.
Batteries are now good enough that in a small volume you can put a lot of energy, and this energy provides enough operability for AMR or AGV to operate for 8 or 10 hours continuously. So finally, it's efficient enough to be used in a robots like this.
So these robots have also the docking stations where they can power, so they can power their batteries.
Exactly. Thanks to the fact that you can manage them from the third party, you can send that AGV to a charging station and perform the charging process automatically without the losing of the AMR from the system, and without powering the AMR off.
Okay, great. So, but apart from technology, there's also behind every technology there's money. Yeah, so there are economical changes and ecological factors that powers all these innovations.
Yes, this is what I wanted to say right now. Economical aspect is always, of course, the most important one in terms of implementing new innovations. So as for economical stuff, in the case of AMRs, we cannot speak about, direct increasing the efficiency of the process, because if we are talking about replacing the process which is done manually by operators, robots do not necessarily always have to replace them in a better way. Like robots will not necessarily do something faster, but it can do something more repeatedly. So this is one of the aspects in which savings are trying to be found by investors or customers. They are
So
trying
less
to
errors. Yes, sorry to
exactly
interrupt you.
less
Less
errors,
errors.
which can cause, for example, safety incidents, or which can lead to malfunctions of systems. So yes, this is definitely one of the aspects that is very visible here. But aside from this, Europe and generally Western side of the world suffers from the lack of hands to work. Not only people who are capable of doing, simple transportation tasks, but also highly qualified personnel, like, for example, forklift operators. So, in order to replace this gap, there is a need to develop and implement solutions like autonomous mobile robots, which could handle the processes related to transport in intralogistics.
So
So, this is
labor
very
shortage is one of the factors that powers the implementation of robots
definitely.
in the industry. Okay, good. Okay, what about the organization? Because I assume that it is quite a big effort from the point of the company that wants to implement these robots to adopt the robots to the workflow, to the mindset, to the environment in which this organization works. For example, to the particular factory floor.
Yeah, as for organizational stuff, I would say like this. If something new appears on the market, there is always a risk that the new thing will not work. So the longer the item or the solution exists on the market, the more trusted it has. So this is what we observe with AMRs. They are present on the market for some time already, and customers see that they are reliable, that systems based on them work correctly. They can be used efficiently, and they can increase the repetitiveness of the process and stuff. So the more installations we have, the more popular they are, and the more investors want to have them. So this is also one of the aspects that we observe on the market. Simply reference, right?
Yeah, okay. So probably clients or customers want to see these installations in action. So just to visit the factory where the systems were implemented and then want to have a similar one at its own factory.
Yes, exactly.
Okay, so just going more into details, could you maybe explain what kind of actions these robots can perform, or maybe what are the types of robots that can have in factory, that autonomous and AGVs and AMRs robots? What are main types of these robots?
Generally speaking, in industrial solutions, there are two types of robots present. The first one is called platform AMR or AGV. The name comes from the fact that they look like a flat platform, and the main principle of bringing or carrying the good is that AMR goes beneath the payload. This can be a payload prepared specifically for a given solution, for a given AMR or AGV. This can be a trolley which has its own legs. So we have to drive with the AMR between these legs. And once there, we can either lift the payload and travel with it, or we can couple with this payload and move with it. Therefore, the transportation capabilities are either based on the lifting or tugging. These robots are actually recently the most common ones due to their, let's say, incomplexity, especially in terms of driving and maneuverability. However, they are not capable of bringing payloads that are located directly on the ground. So therefore, there is a second type of robots used, which is generally speaking the forklift type. The
Okay.
assumption is exactly like we have with manned or operator forklifts. We have forks which need to go into pockets of the pallet, and then the pallet can be lifted up. And depending on the type of the process, there are different types of AMRs like this, from the ones that operate on the level of the ground only, so it lifts the payload only several centimeters above the ground, through the ones that operate on high heights, like for example up to 10 meters or something, and specifically for given environment. This depends on the type of stability of the payload. So we can have a straddle ones with external positioners on site, so it increases the stability. We can have the counterbalanced ones, which have the body heavy enough, so if we lift the payload up there, the whole set stays solid. We can have double fork ones. The assumption is that one side of forks always remain on the ground for the stability, and the other one moves the payload up and down, and so forth, and so on, and so on. And also there is actually the third type of AGVs and AMRs. They are not classified as a transportation carriers themselves, but they can be equipped with, for example, third-party or additional auxiliary automation control solutions like conveyors or lifts or turntables. So they can, for example, form a movable conveying system. We can install something on top of the AGV, which can then pick something directly from the production line and deliver it to the entry of the another production line. So these are the three most commonly met types.
Okay. One question: what are the loads that these mobile robots can handle?
Uh,
How much they
it,
can lift?
yep, this is very general question because
Mhm.
market presents solutions that work on payloads from several kilograms. These are very small AMRs dedicated for fast, very dynamic solutions, for example, for packaging, for sorting, through the most commonly met ones like from, I would say, 150 up to 1000 kilograms. These are the
Mhm.
most often most often used ones, through the heavy payloads like 6-8 tons. But these are very specific solutions, mostly developed specifically for some type of process or some specific customers in branches like building airplanes, building trains, or armored vehicles. But actually, AMRs are present in all types of payloads. In terms of this industry, as we understand, it's usually up to 1000 kilograms.
Okay, just let's move to more the exciting topic, to the exciting topic of how these robots move, because automated guided vehicles, so AGVs, move according to the predefined paths. So you put like magnetic stripe on the floor and they move like this. But if AMRs, the question is not so simple. I think they can move in different directions.
Yes, this is exactly what you said. The very first AGVs that were present on the markets, based on the solution that we have a tape sticks to the floor and we follow this tape. This could either be the magnetic tape, steel tape, or a colored one, which was detected by specific technology, for example, Hall sensors or induction sensors. The main principle of such navigation was that the sensor always tries to be exactly above the tape. And
Mhm.
in order to follow the trajectory, you needed to, glue this tape on the shop floor, and then AGV was trying to follow it. Of course, it was very stable. It had, however, one huge disadvantage, that every time you wanted to change the trajectory, you needed to, redesign the shape of the tape. You needed to take it off and put the new one. Also, there were problems related to maintaining of such tape because, if you have a heavy traffic of forklifts that were crossing and driving over this tape, it was continuously getting damaged more and more. So you needed to, secure it with some specific techniques, blah, blah, blah. So this was problematic in general. In order to, make it more adaptive, more flexible, there was a stage where navigation systems were installed in the AGV. or AMR, and there were markers located around in environment, generally speaking. So every time the sensor sees these markers, the system knew where more or less it was. One of the most common examples was rotating laser, installed on the mast on top of the AGV, and the laser beam was, moving around, and it was searching for mirrors. Mirrors were sticked to the environment surrounding, and thanks to mathematical calculations based on triangulation techniques, for example, AGV could calculate its position and then say where it is and where it could go and so on.
But still, the specific preparation of the production floor was also needed in this case, because this laser scanner was looking for beams, the specific beams that could help triangulate the location of the robot.
Yeah, actually, the main problem here was that there was always an intervention required in order to prepare the environment for the operation. So you
Yes,
always
exactly.
needed to put something in the environment, which was problematic because, in small spaces it was okay. But if you were to, for example, operate the AMR or an AGV in wide space, the big one, it was complex, it was costly, and it generated problems with the maintaining as well.
Good.
And the top of the top, yeah.
What about this AMRs? They need to have some navigation system. I think this is exciting topic of how they exactly navigate in different spaces, like dynamic environment, or like industrial shop floor, for example.
Yes, exactly. So the top of the top was a navigation system that assumed that everything that we need is only on board of the AGV, and therefore the evolution of AMRs started. So we have a scanning device installed in AMR, and this scanning device provides information, measurement data about the environment that is around the AGV. Then, thanks to these things, we can build a map of the environment, and this map is processed only on board of the AGV or AMR, and then having the consecutive scanning of this environment, we can compare what we see, what the AMR sees, with the reference map that was taught in advance. And by this combination, AMR on AGV could assign its position, say, okay, I am specifically in this place, and could then perform the movement in terms of navigation. But the main difference between these previous navigation techniques and this so-called natural navigation is that we do not require anything in the surrounding area. We do not have to put any type of stickers, any type of tape, anything else in order to provide this navigation possibilities.
So, just one thing we need to do before implementing such a robot, AMRs, it needs to scan the environment in which it will be working. So,
Yes, this
once
is
the
one of the
map, this is one of the approaches.
yes. This is one of the things that needs to be done.
Mm-hmm.
Actually, there are two approaches for the navigation. The first one assumes the learning or teaching of the map in advance. This approach is more common for industrial solutions because it's more stable. If we have the map saved or stored on board, then we can continuously compare our current position to this map, which increases the effectiveness of this positioning system. However, there are also approaches which assume that we build the map simultaneously to the presence where the AMR is, and such approach is called SLAM, simultaneous localization and mapping. This, however, is not that widely used in industry due to some limitations related to computational power and the mentioned less stability of the whole system.
Okay, so but how to detect obstacles? Because if the map is already on board of the AMR, it needs to move securely, safely. It needs to detect obstacles or some interactions with humans, for example.
And this is this beauty of integration of various things within Industry 4.0. One of the devices that is used for the navigation component is LiDAR, which I mentioned before. Recently, the type of device that is used most commonly is 2D LiDAR. It's a plain one. It is usually installed somewhere near the level of the ground on the AMR, so it detects the area surrounding the AGV at the height of several centimeters above the ground. Having this information not only supports the navigation system, but also can be combined with the safety system. Safety system is one of the crucial things for all types of machinery used in industrial environments where human operators are present. And from the machine point of view, everything that is within this operation area is treated as an obstacle. Therefore, we do not only can detect something in terms of navigation purposes, but also this thing which shouldn't be there but it is, can be treated as an obstacle. So having this information, we can implement various systems for example, identification of this obstacle with algorithms which will enable or at least try to avoid this obstacle, move around it. If it is a human operator, then usually human operator will simply move away after some time. But if we have some state object, for example, a pallet that is put in front of the moving AGV, this pallet won't disappear suddenly, then there is a possibility to create a subroutine which will try to avoid it, move around, and then continue the work. So thanks to this integration of various sensors, including the ones for the scanning, not only the navigation but also the detection and trying to avoid obstacles as possible. Yeah.
And what about AI? Because this is very hot topic now. What about AI on board of such robots? You said that we have more and more computing power, and we can install more powerful computers on board of this mobile robots. So what about AI algorithms that could help navigate these environments?
Well, this is a very wide topic, I would say. AI things can be used in various branches here. One of the ones which are used now are used mostly in two areas in terms of AMRs. The first one is recognition of objects using vision systems. Having the camera on board, having various scanning devices provides this data fusion, which enables to classify objects and use this information for some process purposes. For example, we can implement an AI solution for recognition of specific goods, and if a specific good is identified, then the robot can adjust its behavior according to this good. For example, if we have something to pick, we do not need to have the information from the process side delivered directly to AMR. We can simply provide the information, go to the station A and pick the item which is there. But this picking of the item can be dependent on the type of this object. So if the AMR appears there, it can use its vision system to recognize this object and then use the specific transportation capabilities, like, for example, robot, which can be installed on top to create a program for specific picking of this item. So vision system is one area. The second one is management of the traffic. This is something that we have not been talking so far. But aside from the hardware layer, which are robots themselves, there is always a software component needed for the management of the fleet or supervising the work of AMRs in general. And since we have various types of data, including the production scheduling ones, there is a vast possibility to use AI techniques here, like, for example, to schedule the production orders, to select the best route for AMR according to current shop floor conditions. Generally speaking, for example, if the path is occupied and we know that it's occupied, we can generate alternative path for the AMR to drive it, and AI techniques can be used perfectly here in order to hasten this process.
Okay, could you imagine a solution where there is an AMR robot with vision cameras that could detect, like, for example, problems on the production line or a leakage in the installation, for example, just going around the shop floor to detect potential problems?
Yes, I think that some limited solutions like this are already present on the market, but this is, in my opinion, the matter of time when such things will appear. That something will be done in parallel to the main purpose. Like, for example, AMR is driving and its main objective is to, bring the good from point A to point B. But since it has the camera installed on board, it can observe the surrounding and, for example, accidentally, it can observe that, there is a problem somewhere out there on the right because the camera has detected it and it recognized the problem. So such information can be generated, let's say, aside from the main purpose of AGV. So yes, perfectly. This is something that will be present in some nearest future.
Okay, great. But you mentioned that there's also a system that is used to manage the fleet of this mobile robots. So I'd like to ask next question about how this fleet is implemented, how to manage a fleet of AMRs or AGVs in a shared areas where there are plenty of objects, people moving, workers, and plenty of robots. Because we talked about one singular robot. It's funny. It's great to see it in action, but what actually is needed here is the system that could help you manage all the robots or the fleet in your shop floor.
Along with the development of robots themselves, there was a need to develop a communication layer which would provide the information what this robot should do. So robot, of course, will perform the movement, bring the item from point A to point B, but it needs to know from somewhere else that it has to do it at a certain moment and it has to do it specifically between some points, for example. So along with this development of hardware, a new class of systems evolved. Recently, they've been called transport management or traffic management systems, TMS, used for internal logistics. The main purpose of such systems is to manage the traffic of AMRs. Usually, in industrial solutions, AMRs are aware of the fact where they are, but they do not make up their own decisions. Do they have, for example, the permission to go through the intersection or enter the production area? Because this can be dependent on the process state or safety, for example. So there is a need for the supervisory control about them. The system monitors where these AGVs or AMRs are and manages the traffic. For example, if two AMRs meet at the intersection, the system decides which should go first because perhaps one of these AMRs have higher priority to drive because, I don't know, the production is delayed and it brings some goods that are needed more urgently. Or, for example, it was there as first and the other ones should wait. Also, there is a problem of the integration of various types of IT systems present on nowadays shop floors. For example, we have manufacturing production systems, we have warehouse management systems, we have third-party traffic control systems for human forklift operators. So if there is a need for exchange of information between these systems and AMRs, there is always a need to use TMS for this purpose. For example, we have an intersection where a human operator meets with the AMR. The question is who should go first? We can, of
Mhm.
course, develop the traffic light installed on top, but there is always, the need to exchange the information. AMR should report, okay, I am at the entry to the intersection, so should I wait? Should I go? I don't know. Let's signal it to the human operator, and then human operator makes up the decision. For example, this is one of the possibilities. In terms of the communication with production systems, usually production systems know what to manufacture, but they do not know how this, manufacturing is related to the transport. So manufacturing execution system can provide information. Okay, I need a lot of material on the station in order to produce something. TMS receives such information and formulates a transport order like, okay, AMR number one, you should go to the warehouse, pick up the lot of material and bring it to production station number 7. So the process continuity can be held.
Is it
And
automated or it needs, does it need human supervision?
no, in general, the point is that it should be completely automated. There is
Okay.
no human intervention here, and that there should not be. This is the main idea and principle of this system integration within modern industrial IT solutions.
So it works autonomously, and once there's a change in production line, the order is generated, and AMRs provides the raw material needed for producing a new item.
Exactly. And such
Okay.
system should also react to changing states. For example, if we have a malfunction on the production area, one of the stations is excluded, perhaps TMS should react accordingly. For example, okay, we see that the production station is not present, so we cannot send AMRs to the station because there will be a deadlock, which is the blockage, right? We cannot manufacture. So perhaps we should reschedule the transport orders to do some other actions. Other AMRs should be sent somewhere else instead of this specific station. So no more problematic issues are generated. Yeah.
Okay, so this production facility would be fully automated without the human intervention. No,
Yes.
so humans will be only supervising the way how it works. Okay, good. So could you maybe say a little bit more from your practical point of view and your experience, how to implement such intralogistic systems based on AMR and AGV robots? So how to start?
This type of project differs a bit from classical approach to design and deployment of automation control solutions.
Mm-hmm.
Still, the main stages remain the same. There is a stage of planning and a stage of commissioning. In order to plan the system correctly, there is a set of information needed, mostly regarding the limitations of the system. For example, how many AMRs do we need to perform the process? What should their transport capabilities be? With what parameters should the AMRs drive? For example, should they drive only 2 meters per second, or should it be more or less? Then, what are the main points of the interest and activities of AMRs? What is the frequency of possible transport orders? What is the logic of these transport orders? This is also something that I had not mentioned before, but transport management system also has the huge function of, handling the transport process. Very often, transport orders are not just simple bringing item from point A to point B. Sometimes more than one AMRs are involved in the task and they need to cooperate. And there must be a control unit which controls this process. For example, we need to perform a swapping operation. This is classical thing present in the manufacturing and assembly processes. Imagine a production station. Just next to the production station, there is a trolley with components, and we use these components one after another in order to perform the process. And there is a moment in which we are running out of these components, so the trolley gets empty. In order to keep the continuity of the process, we need to quickly take the empty trolley and nearly at the same time put the new filled trolley with new components to the station. And this whole process needs to be done within very strict time regime. Let's call it a takt time. If
Mm-hmm.
we make a delay in this step, the production will be stopped because the production line goes on and on. And the point is that it needs to be done very strictly and in a limited time window, right? So you need to synchronize the movement of two AGVs. One should, at the triggering moment, should take the empty trolley away, and the second one should bring the new trolley directly to the production station. So as I said, there is a logic, and this logic needs to be, controlled somehow. So TMS does it. So coming back to the point, in order to design the intralogistics system well, there are two commonly met approaches. The first one bases on the basic analytics. For example, we know that there is a limited number of space. We know points between which the AMRs should drive. We know how often they should do some actions. And we can simply calculate, okay, we need two AMRs, they will be triggered and they utilized like in 40%, 60%, whatever. And this is pretty simple solution. However, in most applications, this is not relevant because mostly fleets of AMRs operate in vast spaces and then they can interfere one with another. This is also something that I have not mentioned before, but the biggest problem with intralogistic solutions is the fact that they are not deterministic. Due to the fact that they can interfere one with another, they can be interfered by the environment. For example, human personnel which goes in front of the AGV, causing them to stop in an emergency manner, or due to the fact that the process can change. For example, we need to pick something with the AMR directly from the production line. It should be there, but the production line didn't provide it to us. So, the whole process is delayed right now. There are a lot of disturbances, and these disturbances cause the whole system to make it unable to, assess in advance, will, for example, the given number of AMRs be sufficient for maintaining and running the process? And actually, in such complex cases, the only reasonable way to, assess the limitations and to design the whole system is to simulate it. And how does the simulation can look? I would say that this is the basic approach for most of companies that deploy and provide intralogistic systems. The main thing of the simulation is to provide these parameters required for the system to work. So we need to know, first of all, what is the layout of the area in which AGVs and AMRs will operate. So customer needs to provide information how the shop floor looks like. This is followed by the information where AMRs should do something. So we are defining or determining the points of interest, like stations, charging points, wait points. Wait points are points in which HVs and AMRs wait when they do not have anything to do. These points are also very important for the process. I'll maybe say it in a moment. So having where, then we can determine how they should work. So we need to determine what are the transport capabilities of such units? Should they lift something? Should they tug something? This strictly follows the information about the transport corridors required for AMRs. So how much space we need for driving, right? Then we need information how often tasks should be performed. Usually, this assumes that customer provides the information how often production orders are delivered, between which stations. Assessment and the logic of such things can be inserted into transport management system, and combined they can be used for the simulation. Simulation can be hastened. For example, we can determine that, okay, within 3 months, we see that there are some bottlenecks, and these bottlenecks, for example, are visible in specific areas where the density of AMRs concentrated temporarily causes the whole system to, get blocked. And the simulation eliminates such bottlenecks at the early stage, but above all, it provides information about this general concept, how the system should work. How many units do we need? How they should drive? What would the logic be? What points are used within the system? And so on and so on.
Is this simulation done on site, or do you use any kind of software like digital twin?
Yes,
to
this is
simulate?
exactly the digital twin of the process. This is actually the designed digital twin of the further process, of future process. However, yes, for this we use the kinematic models, which represent the movement of real AGVs and data exchange with real production stations. So yes, this is exactly the digital twin of the further process, for future process. Also, there is one huge advantage of simulation. If you have the trajectories designed within the simulation, the process of deployment commissioning on site is greatly hastened. Of course, there is always a need to, visit the site. You need to do the scanning, as we mentioned before. You have to build the real map of the environment. But trajectories, like the paths where AMRs are driving, are more or less designed already due to the simulation. So the only thing that needs to be done on site is, minor adjustments, like move path a little bit to the left, to the right, assign precisely where the symbolic navigation point should be located, and so on and so on. In total, the maximum time needed for complete deployment of the system, when you have the simulation prepared well, is like maximum 2 weeks, I would say. This is pretty fast in terms of implementing industrial solutions in real examples.
So if I understand correctly, once the simulation is ready, it takes roughly 2 weeks to implement the
Exactly.
solution
This
on
is the
site
point. Yeah.
at the facility. Okay. We have been talking about robots, but I'd like to ask questions about people, because that's people we have that will have to coexist with these robots that we implement in the facility. How about them? So how to convince people that robots are not here to take their jobs? Maybe that's the point.
I think with it, we already reached the point in which everyone more or less is aware of the fact that we are lacking in hands for work. So robots are always to support the work of human operators, not to replace them. This is
Because
the
there are too
main
many humans. There is not enough number of human workers, so that we need to support them with robots.
Exactly. In terms of AMRs and AGVs, they are also used in industries, in environments in which human operators not always want to work. For example, there are harsh environments like with high humidity, high temperature, very loud ones, noisy ones, where people don't want to work. And this is the place where AMRs, suit perfectly. And if this could be the thing to convince human operators, this is also the point, I would say. As for the cooperation between humans and mobile robots, there is a need to be aware of the fact that these are machines and they are always somehow or potentially, hazardous for surrounding people. Of course, all types of machines which are introduced to the industry need to be safe for humans. Still, there is always a possibility that some incidents will happen. This is the matter of trainings, of increasing the awareness of the fact that this is the operation area where AMRs work. So you shouldn't do some things like, for example, you shouldn't put buckets or pallets on their routes. You shouldn't, move backwards when you are not aware of the fact what is behind you, because there might be an AMR approaching. So yeah, this increasing of this awareness is very important aspect. I don't
Okay.
know if I answered your question.
Yes, you answered my question. So it means that you mentioned you pointed out one very important thing, that the robots can do the work that is potentially hazardous in some very hazardous areas, like
Mhm.
where there's lots of noise or lots of humidity or some kind of chemical substances that can be hazardous or dangerous for people. So it's not only to supplement people, but to replace them in the situation where it is danger to work
Yes, exactly.
in this zone.
I think there is
So
also one more aspect that would be worth of mentioning, that AMRs and the maintaining of AMRs enables new possibilities for the workforce market, I would say.
Mhm.
This is new type of automation control solutions. This is like integration of mechanics, electrics, software of various levels. So there is a need to, have a qualified personnel that would be responsible for fleets of AMRs. And it is more and more often that, factories have their own maintenance services strictly dedicated and assigned for AMRs. I do not like this expression very much, but I heard about something that is called digital shepherd,
Mhm.
which is a
Okay.
person who is responsible for this fleet, like a herd of AMRs and AGVs. So yeah, this is also something that's approaching and appearing on the market.
Okay, good. Just the last question, because I think we had more than an hour of materials, very interesting topics discussed. And I'd say that the lack of deterministic timing. So, because what you said and you mentioned earlier many times, that these AMR robots work in the situations where there is no determination of the process. So, the environment is very dynamic. Something can occur. For example, the robot can meet with a employee, or there could be some kind of obstacle on the way. So how to deal with this, because you cannot foresee every single variation that may
Mhm.
occur.
Of course. Well, yes, as you mentioned, there are a lot of disturbances and interferences of the operability of AMRs. So, in order to avoid them, of course, the main work lies on the side of companies that are responsible for implementing solutions like this. Our job is to, create the system in a way that it's, as invulnerable to such disturbances as possible. We still cannot avoid everything. So I would say trainings and increasing awareness of the process. This is the key to successful implementation of intralogistic systems. This is building of the culture of work, training how AMRs operate, what you can do with them, what you cannot do with them, the continuous improving of qualifications of technical personnel. So yeah, this is something that must follow the implementation of intralogistic systems.
So there's a new requirement for employees in a factory, just how to deal with robots, how to behave, how to co-work with robots.
Yes, I would say it like this, but you can observe that exactly the same situation was present where traditional stationary robots were introduced to
Mhm.
automation solution controls. Like, regular robots are inserted in the cages, and personnel knows that you cannot enter the cage when the robot operates, right? And
They are separated from the
exactly,
humans.
exactly. Yes, they are separated, while AMRs are not. But what I want to say is that there is a specific set of rules that need to be followed. These rules are different, but still, you need to continuously improve this awareness and provide these rules specifically for personnel that works both with stationary robots and autonomous mobile robots.
So this is another step. Just we now need to learn how to deal with robots that in our work environment that are not separated from us, but are co-working with us, like our coworkers. Okay, I think that's all we have for you today. Marek, thank you very much for sharing with us all these insights into fascinating world of mobile robots and sharing your insights into the intralogistics world.
Thank you very much for the invitation and the opportunity and possibility to speak to you.
Thank you very much, and thanks for listening, and until the next time. Bye.
Fabrity specializes in bespoke software development, generative AI, industrial IoT, and data engineering. We build complex solutions for enterprise clients to automate processes, boost efficiency, reduce downtime, and enhance decision-making through effective data analysis. If you have a software project in mind or any questions, feel free to reach out at sales@fabrity.com. And if you have a topic you'd like us to cover or want to join the conversation on Fabrity Talks, we'd love to hear from you. Thanks for listening, and until next time.